Hey, what's up everybody? Today is part 2 of our discussion of oscillator constructions of the representations of sl2R. If you haven't seen part 1, you should go and check that out first. Otherwise, this video probably won't make a whole lot of sense. Okay, super excited. Let's get started. Folks know what a short exact sequence is? Aside from how you define it, it's a tool that folks will use to either talk about quotients of spaces or objects or extensions of spaces or objects, kind of depending upon your perspective. An exact sequence, of course, is a series of maps between spaces where the image of kind of the nth map is the kernel for the nth plus 1 map. So a short exact sequence then is an exact sequence that has only 3 non-trivial entities. Let's call them, A, B, and C. The only moral of the story really is the observation that B is kind of like an extension of C by something that looks a lot like A. We'll get into it towards the end of the video. All right, so last time we discussed the discrete series of representations from the harmonic oscillator using the construction devised by Hirayama and Yamakoshi. One thing we left out was the continuous series of representations, but Hirayama and Yamakoshi did not leave them out of their paper, but I gotta say there's a little bit of trouble with their analysis. Mapping from the module associated to the harmonic oscillator algebra to the discrete series was pretty straightforward. They were in some sense isomorphic as vector spaces, right? Semi-infinite, as you would normally get from modules of a Heisenberg algebra. The trouble that Hirayama and Yamakoshi run into is the same trouble that a lot of physicists are going to run into here, where they just assume, well, okay, if it works in one direction and works in the other direction, we have 2, we just put them together and take a direct sum of vector spaces and see where that goes. And there is a little trouble, and the trouble associated with that involves the vacuum. You see, Hirayama and Yamakoshi just assume that there exists kind of like a pseudo oscillator module that you can construct some states n, where n is now parameterized by the whole of the integers instead of just the natural numbers, and then you can have some operator big N that just spits out the appropriate number, just kind of like a grading. And I guess you could imagine constructing that in the abstract. But when it comes down to concretely connecting this to something physical, which is ostensibly what they were trying to do, the physical harmonic oscillator algebra, that vacuum really causes you trouble, because you can go from 3 to 2 to 1 to 0, but then how do you get to -1, -2, -3, -4? Right? That's or conversely, how do you get the other way from -3 to -2 to -1 to 0 to 1 to 2 to 3 to 4? You have to pass through the vacuum. So the way that physicists, at least in the incarnation of the fellows we've been talking about, they just simply say, well, we don't have a vacuum vector anymore. We just ignore the annihilation of the 0th state by A. But 2 comments. Comment number 1, there's 2 vacuums. So how are you dealing with the fact that there's 2 vacuums, one for the dual space and one for the regular space? Are you combining them together in some way? Like, what's going on? And 2, and perhaps more importantly, The vacuum is a necessary requirement for the existence of the Heisenberg module. The fact that the module exists via the Stone-von Neumann theorem, or the algebraic analog thereof, requires the existence of a vacuum. So yeah, there's trouble. And to give you a flavor for how that trouble comes to be, let's look at a toy example. Right, so before we talk about the toy example, let's just quickly mention the Hirayama-Yamakoshi construction, which creates the operators L plus, L minus, and L0 of sl2R in terms of the creation and annihilation operators A and A dagger, and N, which is A dagger A. They multiply, so L plus is A dagger times some function f of n, L minus is f of n times a. F of n, you might recall, is given by the square root of, n plus m quantity squared plus n plus m plus q divided by n plus 1, whole thing square root. And q and m are the Bargmann kind of parameters in terms of the representation of sl2R. So for our toy example, we will consider something a little bit simpler. Let's consider an alternative function, a different version of f of n, if you like, given just by 1 over the square root of n plus 1. Are you folks afraid of heights? Sometimes I'm afraid of heights. I don't know why it is. Steep trails like this, if you do them enough, that's totally fine, but sometimes an even less steep trail will freak me out. Weird. What's fun about this construction is that you kind of get the normalization of those eigenstates for free. So for example, imagine acting on the vacuum with what we're now calling alpha dagger to the nth power, or now alpha dagger is of course given by A dagger times 1 over the square root of n plus 1, where n is A dagger A. For the case of the vacuum, n evaluates at 0, but we can continue to operate with more and more factors of A dagger, and given that n, the commutator of n with A dagger is equal to A dagger, we end up picking up 1 over the square root of n plus 1, n plus 2, n plus 3, blah, 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 so on, which gives you that 1 over n factorial, which is kind of cool. And, on the dual side too, you also get the same construction for the new alpha acting on the vacuum there, right? Very interesting. But there's a problem. So what's the problem? Well, let's compute the commutator of alpha with this new alpha dagger. What do you think it's gonna be? Wouldn't it be cool if it was 1? Because then you have this automatically normalized states, and you still have a representation of the harmonic oscillator. But that's not what you get. You compute the commutator and you get 0. What? Yeah, 0. And even worse, the reason why the commutator is 0 is because now the new alpha dagger is the inverse of alpha, which in particular means that if we try to act on some state, say n, given by alpha dagger to the nth power, we have 2 possible results. 1, you can act with alpha on the state n, right? And it annihilates, it takes the inverse, right? Removes, if you like, one of the alpha daggers. So you go to the state n plus 1, fine. But because it's the inverse operator, it commutes, and because it commutes, you can send that alpha all the way to the front. And then you get A acting on the vacuum, which vanishes, which means that alpha annihilates all states. Trivial representation. Which is it? Trouble. The camera never lets you know how steep the hill is. And now perhaps you see why Hirayama-Yamakoshi and other physicists of similar type just simply said, well, let's just ignore the vacuum condition. We don't need to worry about it anymore. To hell with it. Because, well, that way I guess you can consistently then talk about alpha acting on alpha dagger, no problem. And it appears that the algebra works, and you can lower all the way down to minus infinity, and you can raise all the way up to plus infinity, right? But is it unitary or worse? And this is something that bothers me still. That 1 over the square root of n, that thing appears in the operators that define Hirayama-Yamakoshi's construction. Let's see what happens when we act with 1 over the square root of n on the vacuum. What do you get? 1, right? No big deal. Now let's act with alpha on the vacuum. What do you get? Well, that's f of n times a times the vacuum. If we assume the vacuum is not annihilated by a, well, we can just commute a with f of n by observing that the commutator of n with a is minus 1 or minus a, right? So that gives us basically a times f of n minus 1 acting on the vacuum. But f of n minus 1 acting on the vacuum gives us 1 over the square root of n evaluated at 0, which is infinity, which is bad. In other words, it doesn't exist, which is another reason why we need the vacuum. Incidentally, Hirayama and Yamakoshi's construction is not immune to this problem either. They also have this factor of 1 over n. You run into the same problem. So they just kind of gloss this under the rug. I don't know if they didn't even look to see or what, but this is a problem. And the root of the problem, as we've been discussing, is that you need the vacuum because it's part of the assumptions baked into the existence of the thing that you're operating on. So let that be a lesson to you. Never ignore your operating assumptions. So, what are we to do with all of this? Well, we still need the vacuums. We cannot assume that there exists kind of a double-sided representation for sl2R yet. How do you get around this? Well, do you ever wonder why folks talk about irreducible representations, reducible representations, and totally irreducible representations? No one ever really talks about, at least in physics land, they ever talk about what reducible representation is not totally reducible. Welcome to sl2R. You see, in some sense, the continuous series, at least when defined in terms of the oscillator algebra, but also harmonic functions and so on, is reducible. It's just not totally reducible, meaning we can't represent it as a direct sum. And we got a hint of this when we discussed both the discrete and the dual discrete representations, because remember, the Hirayama-Yamakoshi operator, L plus, now that really complicated f of n times a, acting on the one state, the one particle state, gave us 0. Similarly, L, I guess L minus hat, right? So alpha dagger acting on the dual one particle state also gave us 0. And this means that we can never get back to the vacuum. Although we can start at the vacuum and operate out in either direction. When we come back in, we get stuck, we annihilate. And so the continuous series, at least constructed this way, is reducible in a sense. And this is why I was asking you if you knew something about short exact sequences. So now we can define the continuous series in terms of a short exact sequence from 0 to the complex numbers, from complex numbers to the continuous representations, and then from the continuous representations to kind of the direct sum of these modules of the harmonic oscillator that we've kind of bootstrapped up to become sl2R modules. And so that was our little tale of the continuous series of the representation of sl2R. I should say that Hirayama and Yamakoshi actually construct like a whole tower of representations based on different powers of the creation and annihilation operators A and A dagger. But you know, they all essentially amount to the same thing. And there is like one fine point that's kind of interesting. You remember the Yukawa representation, which was defined in terms of like L plus given by A dagger over 2, and L minus given by A over 2. Given their construction, you can see here, so the generic value, the generic form of that function f of n for, you know, L plus equals A dagger to the nth power f of n, has the same polynomial in the numerator of its square root, but in the denominator we've got n plus 1 times n plus 2 times n plus 3 times blah 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 so on, which shows you right away that only for powers of 2 do you get the numerator and the denominator even have a chance of canceling out, and they only cancel out for the case where q is equal to 3/16. Still, need it, right? Neato. Anyway, that's all for me for today. Now I got to get down, hopefully before the sun goes away. So talk to you soon. I was just bragging to the camera how like I only ever see like one person on this thing.
Have you done this before?
Yeah, you drop out. You know where Fun Rock is?
Yeah.
Yeah, just pop right down.
Cool.
Yeah,
Awesome.
have fun. Correction. I've now seen 1, 2, 3, 4 people. 4 people on one day. But yeah, it's spring and nothing else is open, so I think the last time I did this, it was like the end of the season. That was fun. Hey, just got a bunch of your comments on the first version of this discussion, and I gotta say I'm blown away. Thank you for your kind words. I guess you liked it. So I think we'll do more videos in this style now that summer is just around the corner. So back to work then.